So this is what we did in class on Wednesday, May 2nd, 2018, shortened due to the building evacuation on Wednesday afternoon. I wanted to do question 7C for those people who were here. We did get through this in the afternoon and certainly did in the morning. I'm going to run through it again here as a review and introduce a new concept that was on my list of things to do today, and that concept is called the reaction quotient, or Q. So we're going to introduce this concept called Q. All right, we're going to look at C to begin with. First thing we're going to look at is C. So I'm going to write this equation here. This is 2IBR. I'm going to rewrite it down here so I can refer to it. This is an equilibrium problem, so we've got double arrows plus BR2. So when you're doing these types of problems, you must first decide if the concentrations that you are given are the equilibrium concentration. So your question in your mind is, are these at equilibrium? Or not at equilibrium? Well, you know that in this case, they're telling us that they put the equilibrium concentrations in a 4-liter vessel starting with. So chances are those are not at equilibrium. I'm going to remind you that 0.3 divided by 4 is 0.075. Since you're giving both moles and liters, you must find the molarity. So the original concentrations of everything here are 0.075 moles per liter. That's capital M, molar. All right, so here's the new idea. Is the system at equilibrium or not? You can tell by just taking these concentrations and plugging them into the equilibrium expression. This is the equilibrium expression. Kc is equal to the concentration of I2 times the concentration of Br2 divided by the concentration of IBR. Oops, there's no 2 there, sorry, IBR. And that would be squared because of the 2 here. That becomes an exponent. So then you plug your numbers in, 0.075 on top. On the bottom, 0.075 squared. So do you notice that this times this divided by this squared is equal to 1? In the problem, it tells us that the equilibrium constant is 2.5 times 10 to the negative third. How does 1 compare to 2.5 times 10 to the negative third? Well, 1 is greater than 2.5 times 10 to the negative third, or you could say that Q is greater than Kc. So is the system at equilibrium? No, it's not, because if it was, Q would equal Kc, because it is a constant. So it's not at equilibrium. Pardon the interruption there, I'll just keep going. So we know that Q is bigger than Kc, so the system is not at equilibrium, first of all, because they should be equal if it is at equilibrium. Q stands for the reaction quotient. Okay, so Q is greater than Kc. So in order for it to be at equilibrium, the Q would need to be smaller, because see how it's bigger than Kc? It's bigger than the equilibrium constant. So what would have to happen to make it get smaller? Well, since Q is a ratio of products and reactants, if these guys went down and that guy went up, wouldn't that make the ratio smaller? So you take the top, the numerator, make it smaller. Take the denominator and get it bigger, and that would make the Q become smaller. You can kind of see it here if I had 2 over 4 and 1 over 8, As the numerator gets smaller and the denominator gets bigger, the actual number gets less. It goes from 0.5 to 0.125. Okay, so numerator bigger, numerator smaller, and denominator bigger makes the ratio get smaller. So that tells us, since we know that Q needs to get smaller, that tells us that the reaction will proceed to the left. So you'd have a minus x here, and you'd have a minus x here, and on this side it'd be plus 2x. Remember, we don't know how much reacts. We just call it x amount. And remember that, I'm going to write it over here. I usually write it on the left side, but remember there are icebox problems. So initial, change, and equilibrium. So at equilibrium, you would have 0.075 minus x, 0.075 minus x, because you start with 0.075, it goes down by x amount. On the other side, you'd have 0.075 plus 2x. All right, now I'm going to take these numbers and plug it into my equilibrium expression. So on the top, you'd have I2 is 0.075 minus x, and the BR2 would be 0.075 minus x, and then 0.075 plus 2x would be squared. And that would all equal the equilibrium constant of 0.0025. Notice I just changed this from scientific notation to regular notation. So now to solve this problem, it's convenient because it's a perfect square. So the square root of take the square root of both sides, and 0.05 then will be the square root of this number. And the square root of that squared is just 0.075 minus x. And on the bottom you'd have 0.075 minus 2x. Or excuse me, plus 2x. That's a plus sign right there, plus 2x. Not sure what all that mess is there, but anyway, 0.075 plus 2x. So what do you do to solve an equation like this? You have to clear the denominator. So you're going to have 0.05 times 0.075. Which is equal to 0.00375. You have to multiply 0.05 times 2x, so that gives you 0.1x, and that equals 0.075 minus x. So now I'm going to combine my x terms by adding x to both sides. So up here I'll do that. I have 1.1x, and then I have to take 0.075 and subtract the 0.00375. And that equals 0.07125. Then to solve for x, you divide both sides by 1.1. And you end up with 0.065. So x equals 0.065. Now you go back to your definitions over here. So if you take 0.065 away from 0.075, you get 0.1. Okay, so 0.075 minus 0.065, oops, x equals 0.1, and that's our answer for that one. Same thing here. And over here, it's 0.075 plus 2 times 0.065, which is 0.13. So 0.075 plus 2 times 0.065 equals 0.205. So that's our final set of answers. All right, so what was the new idea in this problem? The reaction quotient. To use it, we took the concentrations, plugged it into the equilibrium expression, solved for that ratio, found out it was equal to 1. Well, 1 was not equal to the equilibrium constant, So therefore, we know the system was not at equilibrium. So then we decide, well, which way will it shift? Because we'd been wondering, usually we'd say minus 2x plus x plus x. But this time we needed to go left because q was too big, so we just put the minus x on the right. So then the last point, what if you had done it incorrectly and said minus 2x and plus x and plus x? You'd still get the right answer, because when you go take your value for x, it'll be a negative number. And what will happen is you'd go and plug it in, and the negatives will turn to positives, and things will work out properly. So you could try that if you want to do some extra stuff. All right, so that was part 1 of today's class that many of you missed because you weren't here. I'll do part 2 in just a moment on a separate video.